remind you what I was talking about yesterday. I basically told you that I would say something about what goes into the proof of an inequality. Of this form. The sum taken over all real t here. I will not prove it because there is too much to be proved, but I want to tell you about one sort of profound idea that comes in here. And part of the proof, which is due to Konyagin and Kefelec, is to decompose the polynomial in a suitable way into homogeneous terms, homogeneous polynomials. So that is a non-trivial business here because this is not so easily. This is not so easily done because you have to take into account certain number theoretic aspects of this object. But we let's accept that, and so a main ingredient is the following. Estimate for homogeneous polynomials. On dm. So what we do is we look at polynomial like this, which is a homogeneous polynomial, and if we well, let me begin by saying something which is obvious, namely if we take the square sum of the coefficients or the norm of the coefficients, the L2 norm, then clearly this is less than or equal to, let's call the polynomial something, f of z. Then this is less than or equal to the infinity norm, the supernorm, the polydisc. Now, I ask the following question: can we have a similar inequality if we change 2 to another p? Of course, we have to pay a price here, but is it possible to have an inequality like this for some p less than 2, that we increase the left-hand side when p becomes smaller, so we have to pay a price here. So what I require is see, depending on the degree, but not on the dimension. And the answer is yes, of course, since that's the question. But to see what is the best we can do? We can go back to our Shapiro polynomials. Remember, our routine so we had Q, which was 2 to the k for a suitable k, and then we constructed a polynomial P with Q to the m coefficients, which were either plus or minus 1, and with infinity norm bounded by q raised to the power m plus 1 over 2. So that means that if for this polynomial we would have this sum equal to the number of coefficients divided by p. And since q clearly depends on the number of variables, I think the relation is that q is equal to n over m. What we have to require is that the exponent here is larger than the exponent here. So we need, therefore, we need m plus 1 over 2 larger than m over p, which means that p has to be larger than or equal to m 2m over m plus 1. Right, because otherwise we will get out a q here depending on n. So there is no hope that this constant independent of n. And guess what? This is the right p. So, and this is what is known as the Bonn-Castiglione inequality for homogeneous polynomials. Says that we have in fact, the best we know about the constant that comes here is that there is some universal c raised to the power m times infinity norm of the coefficients of the polynomial. This is really a remarkable inequality, and it's very old. It goes back to 1931. But with this precise estimate, this exponential growth of the constant is shown in the paper that I mentioned yesterday. And, 5-author paper. So and it turns out that to get optimal estimates in different situations, like for instance in this to get the optimal estimate for S of n, you actually need this exponential growth. So the main point is that you have a constant which does not depend on the dimension. Okay, so I'm planning, as I said, just to mention one profound idea which goes into the proof of this inequality, and that is the idea of relating these polynomials to multilinear forms, to go from polynomials to multilinear forms, which it seems you, at least the proofs I know, use that fact in a very essential way. So essential to relate it to multilinear inequality. So, let E I goes from 1 to n, the canonical basis in Cn. And this starts with an inequality of Littlewood. 4/3 inequality. It says that if B is a bilinear form, so we have a bilinear form from Cn across Cn into C, then we have the following inequality that the coefficients with respect to these spaces four over 3 here, 3 over 4 there, is less than or equal to square root of 2 times the sup of the form over the product of the two polydiscs here. So let me write it like this. So that's just B infinity is sup for set W in Dm. So this was first proved by Littlewood, and as you see, 4 over 3 here corresponds to this should be P, of course. It should be the P that I came up with here. So 2m over m plus 1, m plus 1 over 2m. So, if m is equal to 2, it's 4 divided by 3. So it's exactly the same thing as we have here. So this was first proved by Littlewood. Then Born-Blust and Hille extended this to multilinear forms. So Born-Blust and Hille proved Littlewood. This is from 1930. And Born-Blust and Hille proved that if if we have a multilinear form, so we have m copies here of Cn, then for such a thing, we have v of e j1 e up to jm raised to the power 2m over m plus 1, and then, well, m plus 1 over 2m here. This is less than or equal to square root of 2 raised to the power m minus 1, and then the sup norm, which is defined in the same way of the form. I should say here that recently there have been quite a bit of activity in trying to improve the constant here, and successful also. So let me mention a very recent paper by, well, this is also with many authors. So, many authors with long names. Serrano. There are several papers, and they also consider the real case, and it seems that the best result is in a paper that is to appear in Journal of Functional Analysis in 2013, actually. So, and the bottom line is that the constant here, you can actually get m to the d for some constant, let's say m to the a for some a. So it's not, it's the best we know is that it's not exponential growth, but actually polynomial growth of the constant. And I will not say more than this, that there are papers out there explaining how this applies in quantum information, but I will stop there. I'm not able to say much more about that. So anyway, there is a lot of interest in this inequality. Now, what about this inequality? Is it possible to have something better than exponential growth? This I don't know. It would be interesting to know, but I don't know. Okay, so what's the point here? Well, the point is that we can move between polynomials and forms because of something which is known as polarization. So let me just explain what this is. Polarization. Which is really a one-to-one correspondence between homogeneous polynomials. And symmetric multilinear forms. And not only that, it is a one-to-one correspondence which comes with estimates, so that you have control of the infinity norms of the two things. So I should say perhaps a one-to-one correspondence with estimates. in one direction, it is absolutely clear how to get from a form to a polynomial. I mean, if you start with a form, clearly if you just put the same z in all m places, you will have a polynomial which is homogeneous of degree m. So this will clearly be a homogeneous polynomial of degree m if I have m vectors in my form. So is clearly is a homogeneous polynomial. Let's say m homogeneous. An m homogeneous polynomial. If B is m linear. What about the other direction? Well, the nice thing, and this was actually invented by Bonobust and Hille, is that there is an integral formula that both gives us the form and the estimate. And the formula is like this. So let's write up the following. We have m vectors going into the form, and we write an integral. Here I put m factorial, and then I integrate over the polycircle Tm. I take my polynomial, and I plug in here a linear combination of these m vectors. And then I place here my m variables, the conjugate of them, like that. And then I integrate with respect to normalized Lebesgue measure on the torus. Okay, so that means it depends on m here, and that's just like a zeta, like that. Well, why is this fine? If you think about it, since you integrate against this, you will only pick up the first order terms with respect to zeta 1. I mean, if you when you start taking higher powers, this will be cancelled by this one. So this means that it will actually be linear in each of these vectors, z1 to zm, because of the orthogonality. So that's one thing. Clearly it's symmetric. I mean, you can change the order as much as you like. So we have a multilinear form. It's symmetric. So the only question is, will we get back to P if we do this? Okay. How to get back? Well, we just put the same vector in all places. And that gives us a linear combination of Z1, Zm, which by homogeneity can be taken out with a power of it to the m. So what I'm trying to say is that we get, well, P of Z 1 over m factorial, and then we get the integral of Z1 plus Z1 up to Z, or zeta I should say, zeta 1 up to zeta m raised to the power m. This goes out, I repeat, it goes out because of homogeneity of the polynomial. And then integrated against Z zeta 1 up to zeta m p mu zeta. Okay, now again, by orthogonality, the only thing you have to care about here is the term which contains the product of the coordinate functions. Okay, so what is the coefficient of that? And of course, I kept that in mind when I put 1 over m factorial, but because it is just m factorial. Okay, so this is equal to P of Z, because
So it means that P is in unique, yes? Immediate.
I'm sorry?
P is in unique, yes? Immediate.
Yes, 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 yes. This will be like this, which is an easy exercise to check, plus terms that we don't need to care about, plus other terms. Which will vanish. And the fantastic thing now is that, as I said, you get immediately an estimate. Because, well, here you have a linear combination of vectors which we assume lie in Dn. These guys are in Dn. The combination of them, the linear combination of them, sorry, will lie in M Dn, which is just by which I just mean that I multiply each element here by m. Okay. Is it clear? Okay, so that means that I can simply estimate the p here in terms of the infinity norm on this set, and then I get the factor m to the m times the norm of p, again by homogeneity of the polynomial. So I get, well, first of course I get that the norm of the polynomial is bounded by the norm of the form. That is, of course, immediate. And then I get that the norm of the form is bounded by m to the m, which is what I get out here. When I integrate over and take absolute value, I get just 1, because it's normalized Lebesgue measure. So I get m to the m over m factorial. And this is something which grows exponentially. I mean, it is less than or equal to e to the m. So we don't lose much in the sense that we have only exponential growth. Is it okay?
Yes.
Yeah. So this is the basic, well, the profound, one of the profound and essential ideas in Bodenblust and Hille's work.
A lot of cancellation in this integral, so this is very rough. It looks very rough.
Okay, so then the challenge for you is to come up with something better, which would be fantastic, because then we perhaps we could improve, and instead of having exponential growth of the constant in the inequality, we could have something better. But I don't think it's so easy. But of course, it's a very rough estimate, and surprising that you get it so sharp when it's so rough. Yeah, I could say something about how this came up, this Bono-Bluzille work. It has something to do with the Dirichlet series, but I'm planning to say something about that tomorrow, so perhaps I can leave that for tomorrow and go to the next topic, which is something completely different. So far I have been discussing different kinds of homogeneous polynomials, some very concrete examples, some general properties, like the Bono-Bluzille inequality. Now I will leave the homogeneous polynomials and consider a completely different situation and problem. So the topic is what I will call, and it will become clear, GCT sums from Poisson integrals. And this is what I'm saying now is to a large extent based on a preprint with Christoph Eisleitner. Which you can find on the archive. Okay, so to motivate what I'm going to do, let me, and before I get to the polynomials, let me say something about kernels that we all know well and appreciate, namely the Zeug kernel. One over 1 minus z. Well, maybe I should put a name on it. K z of w 1 over 1 minus z bar w, and then we have the Poisson kernel. P z of w. Well, this is a reproducing kernel for H2. So if I take a function in H2 and take the inner product between f and this kernel, we all know what we get. We get the value of the function. But what I'm most interested in now is that we get the precise estimate. Well, let's, yeah, we get, if we square it, we get 1 over 1 minus c squared times f 2 squared. If I take some L1 function, let's say u on the unit circle, integrate against the Poisson kernel, I get, well, what is roughly the best I can say. If I take the largest possible value of the Poisson kernel, I get that this is less than 1 plus mod z over 1 minus mod z times the L1 norm. And if we think of these pointwise estimates when we go to the unit circle, of course, it doesn't make a big difference that we have a square here and we don't have a square here. We think of that as basically the same thing. Now, if we go to several variables and even to infinitely many variables, then this picture changes completely. I can simply the analog in the d-dimensional situation of this is just a product of guys like this. So explicitly, it's a product. And likewise for the Poisson kernel, just a product of one-dimensional Poisson kernels. Okay, so if I do the same, well, what do I get? I get the same thing, except I get, in one situation, I get the product of these guys. This is this one for the other one. So this changes into this, and then of course the function there and so on. And for the other one, I get the product 1 plus mod z j. Now, if I want to go to infinitely many variables, I have to take care about the think about the convergence of these infinite products. So when d equals infinity, okay, in star, if the sequence Zj is in L2, while here I need to require L1. We need L1. So you see, in some sense, the picture changes completely if you go to infinitely many variables. Sort of the action takes place not at the boundary of the circle, but actually close to zero, because you need this convergence of the series here. So it's really two very different kinds of estimates. And the next thing I want to discuss is something quite interesting that takes place sort of in between. So sort of in between L1 and L2. Okay, so that the game I want to play now is the following. Right, be patient. You will see why I want to play this game. So let script P with sub n be the set of all polynomials in as many variables as I wish. I'm free to choose as many variables as I wish. In as many variables. I mean, we can think of these as polynomials defined on the infinite dimensional polydisc. As many variables as we wish, with at most n non-zero terms. Okay, now what we do in addition to that is to choose a point or rather a sequence T and so on in D infinity, which just means that all of these guys are less than 1. And in fact, what I will require is all of them positive, and I want them to decrease. This is just sort of for convenience. Then clearly it makes sense to speak about the poisson kernel at the point t, especially if I integrate against these polynomials, because then it's just a finite dimensional polydisc that I integrate over, and using multi-index notation, it just means that I pick, well, the first a certain number of the t's here, and so I have only finite products all the way. So now I want to study the following object or quantity. Lambda, define lambda t of n to be the sup of, well, this is all. I take square of the polynomial. I integrate against the poisson kernel at the point t, and I divide by the norm of the polynomial, the L2 norm squared. And I take sup over all f in P n. If you worry about f being 0, all non-trivial, we add non-trivial. So be patient. There is a reason I want to look at this. Of course, from the remark I mentioned here, this is interesting only if t is not in L1. Okay, interesting. Only if this sequence t is not in L1. Okay, now the first thing I would want to say is that this is a quadratic form, and we can actually compute the matrix.
Can I ask a question?
Yes, yes.
If t is not in L1, how to what is e?
This makes perfect sense because I have this is a polynomial. So I take only a finite part of the sequence. So no problem. So the point is that it depends on n. Yeah. Right. So let's see now. So explicitly, this is I mean the polynomial is something like this: a alpha z to the alpha. So what goes into this thing here can be written as a alpha times a beta bar over all the indices alpha beta, and then with a certain matrix here. And the question is, what is this? So let me compute it. Okay, this is of course just the Poisson integral of z alpha z beta bar Poisson kernel. Well, sorry, it should be w because I have z downstairs here. let's do this computation in one variable because that's much easier. Okay, so if I have on the unit circle, I take w raised to the power j, and I have here w bar raised to the power k against the Poisson kernel. What is this? Well, this is just an exponential, right? And it will either, depending on which is the larger, j or k, it will either be analytic or anti-analytic, but it's still harmonic, right? So I get the value of this harmonic function at the point, well, t. And the value of this harmonic function at the point t is just, since it's positive, t is positive, it's just t raised to the power the absolute value of the difference between j and k. Right? This is because exponentials are harmonic functions. So this, of course, applies to each of the variables here. So this becomes just, and now I have to do something, unfortunately, with my notation because I want very much to use the same notation here. And now from now on, this is a new multi-index. Okay, I take alpha 1 minus beta 1, absolute value, and so on. So let's perhaps write it like this, j, where j goes from 1 to infinity. Of course, only finitely many of these will be different from 0. So that's very nice. Very simple expression for this. And what is even nicer is that if I choose t in a special way, choose, interesting choice, of t is to let t be the prime numbers raised to some negative power. Pj primes. Okay. Then, what is this? Well, we can for a moment forget about the alpha because that's something that, let's just set alpha to 1. So Pj, or P minus 1, or let's write it like this. I think you understand what I mean. What is that? Well, as we did yesterday, we can associate now. Well, alpha now is extremely unfortunate notation, of course. Sorry for that. Maybe I can change it to mu here because okay. I will soon change this one into mu. Well, let me do it right away. Okay. Now, remember, so any integer can be written in this way: n raised to p mu. Okay. So what is this quantity then? This is well, since let us do a small computation here. If I have two numbers a and b, then I certainly can write this as a plus b minus the minimum of the two guys. Or alternatively, minus 2 times, sorry. 2 times the minimum. So a plus b, that just means that I take, okay, so let the two numbers be n and m. So that means that I take here n times m, and downstairs, if I take the minimum of the two, it means that I take the greatest common divisor. So downstairs, I get the greatest common divisor of m and n squared. I could also have said that this is the ratio between, this is actually also the same as the maximum of a b minus the minimum. So I could also have said that this is the ratio between the least common multiple and the greatest greatest common divisor. So it means that our matrix is really a rather interesting number theoretic matrix if we choose this particular sequence Pj. So perhaps that's enough for this first lecture today. So now I will tell you a little bit afterwards about how we can estimate things like this, and we will see that this is very non-traditional estimates with Poisson kernels. So this means that if we choose t to be this, or any power here, and if we choose all the coefficients of the polynomial to be 1, then we get a sum of this form. Greatest common divisor of nj nk raised to some power 2 alpha, and downstairs nj nk, and j and k goes from 1 to n. So I put all the coefficients, all a alpha 1. Then this becomes this. I mean, this expression here becomes that. I perhaps should also divide by the norm, so that comes out as 1 over n. And as you might guess, this is where we started. So I did things in the reverse order here, but I did that perhaps to stress some function theory here, which I don't completely understand, but which I find very interesting. So in any case, let me say a few words about this. Sums like this have a fairly long history, and it begins with the problem of Erdős. So Erdős, so let's call this simply, we take the soup now, or all possible distinct n tuples of integers, okay? And let's call that gamma. Well, maybe we can call it in accordance with the notation here. Sorry? P to the minus alpha. Okay. P to the minus alpha is the sequence in the polydisc, which comes from the prime numbers. Okay, so Erdős posed the problem to compute or estimate gamma p minus 1. And that is quite interesting because we are now really on the edge between, remember, between L1, for L1, I mean 1 over p is a very slowly divergent series, but it's not L1. So, and then this problem was solved by Gall in 1949. It was actually a prize problem of the Dutch Mathematical Society. Gall showed that this quantity, gamma p to the minus alpha, p to the minus 1, behaves as log n squared. And that is a fantastic paper, not so easy to read, but it rests on some combinatorial arguments. It turns out that the techniques that go into this paper mainly don't work for this problem. And it turns out that for this problem, it is very useful to go to the polydisc. I mean, for alphas different from...
I'm sorry, this log n is a finite sum of the series 1 with b. Is it some connection?
Yes, of course. Yes. There is a connection. Clearly, there is a connection. But I mean, it's not. It's not on the surface.
Yeah.
Okay. So now it turns out that in order to, so when you have this connection to the polydisc, you might think that we can forget about the combinatorics that go into Gall's paper and just work with estimates on the polydisc. But it turns out, it seems, that you have to do some combinatorics to deal with the problem on the polydisc. So there is one very basic idea in Gall's paper that is still very useful. So let us now simply specialize to... So in general, consider gamma t of n defined for general t. So it just means that instead of looking at all matrices or all coefficients, possible coefficients, I just specialize to all the coefficients being equal to 1 for a general t. So this means that I'm looking at sums like this: S of t n is sum t beta j minus beta k with beta j, beta k in a set of an n-tuple of multi-indices. Let's call that B. So B. And I want to find out when this is, and let's divide by 1 over n, or divide by n. Okay, so when is this large? Well, somehow, perhaps you may think that if I have, if for some multi-index I also have all possible subsets of this multi-index, that's probably a good thing if I want to make this large. And this was certainly what Gall found out, that in terms of integers, if you have one integer in your set of integers, you should have all divisors of this integer also in the set. So let's, for following Gall, we say that this B is canonical if the fact that beta is in B and mu is a multi-index smaller than beta. This inequality takes place entry-wise in the multi-index. Then also mu is in B. Now, it is almost true that canonical B's are the best, but not quite. But it's close enough, so we can prove the following lemma. And this is not quite Gall's lemma, but it's sort of after Gall, I would say. For any B, there exists canonical B prime such that S of, and now I have to do a little extra. Here I put 2t prime is larger than the guy I started with. So I have to pay a small price for moving from a general B to a canonical B prime, and that is a factor 2 here. Okay, you may say it's possible that this is not in D infinity, so let us assume, to simplify things, that 2dt is also in. Of course, when you go to the prime numbers and so on, you have some trouble with that, but this is a minor thing. This is a combinatorial result, and I thought I could try to convince you that it is true. I mean, this kind of arguments are not so easy to write down, but can be easier to visualize, perhaps. So these multi-indices that go in here, let's say in our set B, they consist of, well, it could be many here, so it's bj1 and so on, bj, say L, and so on, and from some point on they will be 0. Now let's fix one entry L. So it's natural to do this entry-wise. So we make the reduction to this canonical B entry by entry. Okay, so if we once we have fixed L, we can group the beta j into, well, actually equivalence classes. Where two of these guys belong to the same equivalence class if all the other entries in the two multi-indices are the same. Okay, so beta j, beta k belongs to the same class of multi-indices. Well, what should we call it? Let's call it A. If beta j, now I'm running out of letters, nu, is equal to beta k nu when nu is different from L. Okay, so when we compute this sum, and what I would like to do now is to reduce in all these equivalence classes, I simply want to make the entry for each of them as small as possible. So maybe I can try to make the following picture. Well, now I remove the, well, okay. Okay, so let's make a picture of this, let's say, one equivalence class. So I don't think about what the other entries are. I mean, they can be whatever they want. Now, but of course, the elf entry that goes, we can think of maybe as a tower. So maybe we have 1, maybe we skip 2, and then we have 3, and then we have 4, and maybe we have more up here, something like this. Okay, so this is just the first multi-index, the second, the third, and so on. And we have a sort of a tower with holes, because it's possible that we missed some numbers in between. Okay, so what I want to do is simply to move the tower, remove the holes. So I simply move all these entries down. So that, how many did I have? I have 1, 2, 3, 4, 5, 6. So I simply get a tower like 6. There should be. This is the algorithm for moving to a canonical situation. Now, what we need to do is to compare multi-indices from two different equivalence classes. It's clear that for the relationship between the guys that go into the same equivalence class, we just do better by making it more compact in this way. But what if I have two different towers next to each other? Well, if you think about it, the optimal situation would be to have the longest going down like this, and then the shortest of the two towers in this symmetric, if possible, or at least in the middle of the other tower. Is that clear? I mean, you want the distances to be as small as possible. Of course, if they are both spread out, then the distances between the different boxes here will be large, and you want them to be small. And the smallest possible you can get is by having a situation like this. And this is what Gall actually proved, that this is optimal, and this is the best way to put to have this sum minimal. Maximal. Now, what we want to do is not this, but we want to have rather this situation. So I have the large tower, and I have the small tower next to it like that. Okay. So that means that it's fine with, of course, with these and these distances. But here I will have the distance from let's say, from this guy to this guy. I will also have on the other side. Now, if you think about it, I basically lose a factor 2 if I put it here. You have to sit down and think carefully, but you basically you get 1 from each side here. Here you just get 1 from this side, so you basically lose a factor 2. So when going from the optimal situation to this, you lose a factor 2. And this you compensate by putting the 2 into the t. So that's roughly the visual proof of this this combinatorial lemma, which is painful to write down, but this is the idea of it. Okay, so then once you know this, now we stepped out of the polydisc, right? Now we go back, because now we have a tool. We have some information. So if B is canonical, then we cannot have more than n minus 1 only at most n-1 variables. Right, because all smaller multi-indices have to be there. So in particular, you have to have no, sorry, not variables. Sorry, indices. Let's see now. How should I phrase it? Maybe I should. Maybe let me introduce some notation here. Yeah. So let the support of the multi-index be the number of non-zero entries. And the total support then total support the number of points in no, I'm sorry no, I'm sorry, this is nonsense. It's getting late. Let's try again. So that's just a set. Of course, the support, excuse me, is the set of those integers L, such that Pj L is a non-zero. That's of course the support. Okay. Then let's try again. So if you take the union of the supports and take the cardinality of that I claim it must be less than or equal to n-1. Because all singletons will have to be in the support. So the sequence which is 1 at L and 0 at all other places have to be in the support. So that's why we get this. And we also get that the size of the support of an individual multi-index cannot be very large. If the support, because, well, let me write the estimate. It must be less than log n divided by log 2. Right? Because I just take all the subsets of a set of size the support, and that set has cardinality 2 to the n. So in other words, no, I'm sorry, n must be larger than 2 to the support of beta g, the power set. This is very interesting and important information for us, and with this information,
this is because just any prime number is bigger than 2.
it has nothing to do with prime numbers. It's just that I take I take the support, okay, and then at least in the support of the multi-index, I have to have 1s at each of the entries, and then I have to take all possible subsets, and this is the power set. So it's 2 to the size of the support. Sorry. Yeah. So if each individual, this is very important, each individual multi-index can have at most these many, and this is the total number of size of the support. Okay, so after this combinatorial argument, giving us this estimate, we can go back to the polydisc. Now, how should we do that? Well, this Poisson kernel looks like this. Yeah, it's a finite sequence because set J is it will be finite here, but it turns out that basically, since this is in L2, we don't have to care too much about it, and we think of this as the absolute value of this fellow. And this we now write as a, well, basically as a geometric series. So it means we write it like this. Where the multi-index beta will simply range over whatever number of variables we have here. So let's say beta larger than, let's see, yeah, probably I should, let's say, in the total support then, actually, yeah, of the whole thing. So maybe we could call that B is used, maybe is this total support. So this is how we can write it. So this means...
I'm sorry, here is the size of T. T is a number, yes?
T is a number. It is a number, so it's multi-index notation, T to the beta. And this is the support. This is a sequence. T is a sequence.
Yes,
I raise it to the... So now to estimate things, what we actually do is to just multiply this series with our polynomial, and we use the way we know how to compute L2 norms. We just take the square sum of the coefficients. Okay, so we get I forget about the 2 now. We don't care about the 2. We have a. We assume we have a.
Sorry, why is
yeah.
this equation? Some inequality or something like this? Because you have infinite series, yes?
No. Here I have an infinite series, yes. Here I have a finite product. So this J is just over. Well, I probably have some trouble with my notation now.
Yes, because I don't understand.
Yeah. Okay. Let's see now.
T is the sequence, so you have Tj in each product. In each vector you have Tj, yes.
Yeah. Yeah, there is something funny with my notation now. I probably... Okay, so let's... yeah. Right. Let's do it in the following way. This notation is very unfortunate. Since I have, so I know that I have only n-1 variables actually involved here. So it means that I can go from, let's say J goes from 1, and of course since it's a decreasing sequence, I can assume that it is just the n-1st. So it's n-1. Like this, and then it means that I take here over all multi-indices such that the support, its notation becomes not so nice. Support of Bj is contained in okay, let me introduce the following notation. So let R of beta be the largest L, such that beta L is different from 0. Okay, so I take over all betas such that R of beta is less than n minus 1. Yeah. Then this becomes the sum. Now over the same set here, and I don't repeat it. And what comes here? Well, that is what that we get when we multiply this fellow with the polynomial, and that means that we get R to the beta minus beta j, and now beta j belonging to beta j less than beta. This is what we get. I simply multiply. Remember, I probably should recall what the polynomial is, but the polynomial is set to the beta j, or beta j is in B. So I just multiply this guy with this guy, and out comes come these coefficients, and the square sum of these coefficients is precisely what goes into this one. Probably I forgot 1 over n. So now the question is how to estimate this, and it turns out that because of these two things, this is quite doable. So what we do, and probably I shouldn't spend too much time on that because it's hard to follow, but I just want to mention that you split the sum into two parts. One with betas with large support, and large support means a constant larger than 1 times this upper estimate that I have here. So that means larger than some xi times log n. And this can be dealt with quite easily because now, because of the size of the support, all of these guys will fall. And then for the rest, small support. So, yeah, it's the result one gets is something that don't make you excited, probably, but it's very useful, and it's nice because it's we are back to almost back to the Schur test. So we get sort of a Schur test result. Out comes following theorem. And now I assume that assume 2t is in the infinity, and assume and let Vj be a sequence which is positive, decreasing, and so one and and Vj larger than Tj squared. So what do we get? We get that this quantity, which I call gamma t of n, is less than or equal to what is Rn? Well, I should probably tell you, but let me write it first. And then plus something which usually is quite small. Where C is some absolute constant. Rn, I promised to tell you what that is. Rn is the integer value of this number which I've decided to divide small and large supports between. Okay, so you see here comes L2. So whenever it is in L2, we can forget about this. And then it is, in general, up to us to choose a good Vj. This may look messy, but if you look at the concrete situations with these primes as the prime example, you get so it's as I said, it's really quite analogous to this with the Schur test. You use the Cauchy-Schwarz inequality in a somewhat more sophisticated way, but not so different. You plug in a suitable sequence which goes into the Cauchy-Schwarz, which you just plug in a similar way, and now we get choosing. I should see what I choose. Yeah, basically choosing it's almost true what I'm saying now. I mean, you basically have to think about the first here, and the best thing to do most of the time is to choose Vj to be equal to what? Tj. So then you will have the same in both of these places. That's most of the time the best thing to do. We get essentially best possible results for these gammas. when you have p minus alpha downstairs. So you get things like log n 1 minus alpha, and then you get a log n minus alpha. This is when alpha is between 1/2 and 1. So here we are on the edge with L1, here we are on the edge with L2, and things become more complicated on the edge. So here we have a constant c log n, and it's quite remarkable because it's the same factor that we have in this ball we had yesterday. So this is when alpha is equal to 1/2. And something quite abrupt changes when we go below, then we are sort of out of the most interesting situation. Then we get a rather rough thing. 1 plus little o of 1. 1 minus 2 alpha. So you see, the most interesting, as I said, the most interesting situation takes place between L1 in L2 minus L1. And in fact also on the edge it is quite interesting. This is best possible even with a constant there. This I don't know if it is best possible. It's possible that you could have lost a factor log n. And then, of course, I should also tell you that we don't invent formulas like this because we like many logs and so on. They actually go into some interesting problems in approximation and in questions about dilated systems of functions. But I think we're all getting tired, so perhaps I can just mention very briefly that in a very recent preprint, Istvan Berkes used these estimates to show a couple of things, and let me mention one of the things he did. He showed that if you have a function f, and you take dilations of it like this. It's a periodic function. F is a periodic, say one periodic function. F one periodic. And F is in the set of functions of bounded variation. So the question is, which has been studied by several people, is when can we be sure that something like this converges almost everywhere? And what Berkes showed is that this happens if, I mean, you should keep in mind the Carlson theorem. I'm sorry, it should be an AK. E is in L2, that's Carlson, right? That's Carlson. Okay, so, but if you have a function, so that means when you have the trigonometric system here, cosines or sines, well, then you are in the Carlson situation. Okay, so what do you have to assume here? You have to assume that it is a little better, but not much. And then with the gamma here, which is larger than 4. And this sort of ends a long story, because Berkes also shows that, well, if you have a gamma which is, I think, 2, then you cannot do this in general. So this is actually as sharp as you probably can get. So there are good reasons that people are interested in estimates like this. Okay, so well. I hope I have convinced you that polynomials on polydiscs can be quite interesting, and that the topic has many interesting connections, and that things change quite a bit from what we're used to on the disk, and that the infinite dimensional viewpoint actually changes things completely. So that's it, I think. Thank you.